Okay. All right. Let's do some work. Today we're going to try and get PDHG running. We might start off with something simple to get started. So currently, for both the Tikhonov regularization form and for the minimization over the sphere, the apply A top and apply AM are both doing the same thing. So we're just, at some point, I think we're going to do it right now. At some point, we're going to move that apply M out of into this function that calls both forms, like we did with apply W. Okay. There's a problem at line 64. Right. Problem at line 258. This I think we could resolve pretty easily. But now we can set a breakpoint. And now let's see if we get a reasonable image but lambda equals 1. Sample mask. Okay. Let's see if that breaks. Looks like it does. Not enough inputs, of course. Wait, what? Forgot to put an at right there. Okay. So we still get the high quality image out. And so we've moved apply M out of these subfunctions, which is just a little tiny cleaner. Looks like we're not using N coils. We'll bring it back if we need it. Now, the square root of lambda is the thing that prevents us from moving a bottom out of here into the super function, into the calling function. Apply W is never used by itself. It's always used with apply W minus I. And in this other function, we actually have apply W minus I. Let's move that out too. Now here we don't pass in apply W, but apply W minus I. Up here in do checks, we can check W, apply W and apply W minus I. Okay, those adjoints pass. A simple check. That's also a little bit cleaner. I'm feeling accomplished. How about you? We're never going to call prox G2 from PDHG. We're just going to call prox G. So prox G requires this second parameter as an input. But prox G2 does not. So we don't actually need to pass that in. Now both here and here we have fs, right? How are we handling that? Okay. We're moving fs out. We're moving it into the calling function. Let's check fs. If I put the cursor here and say find w, replace with fs, does that do it? Hey, that's great. Okay. Okay, let's see if this works. Did I not set it up to do checks in this calling function? Hmm. This sum is, oh, I see. So fs takes in something of size image. Not size k data. Fs passed. Undefined variable or adjoint a top. That's because a top has been replaced by m and moved out of this function. Code still seems to be working. So why did I do all this? The biggest issue for me is that when I've got replicated code, that is a copy of code, the same code in two different locations that does the same thing, if I fix a bug in one location, I almost always forget to fix it in the other. I can never remember where that same those same copies of codes exist. I don't like that. So when I can, I just make one copy and use it, which is what we just did. So to call this out top, I'm going to call this MFS in. I'm going to call this MHN. Back to this A bottom thing. It's almost the same, right? The only difference is the square root of lambda. Well, if square root of lambda were set to 1, then this function, A bottom, would be the same thing here. can do that. And then eventually both of these functions won't need to take in all of these different function handles. Rather, they would just take in apply A. That seems pretty nice. The issue is that it's going to be a little tricky. Like, when do we set lambda equal to the square root of lambda equal to 1, right? Well, it goes back to that set of if statements we've been working with. I'll show you what I mean. We're going to do it. This is almost just apply W minus I. This is in the Tikhonov. Like, already, look, even before I commented out that function, it looks like we're currently not using SMaps because SMaps is only used in apply FS. So we can already get rid of that input argument. A bottom. It's just this. That's just apply W minus I with the square root of lambda. Oh shit, I put it in the wrong place. I could keep it like this, but I don't want to. I just want to put square root of lambda times blah. So this is apply W minus I. Now square root of lambda is in that function. Okay, so this is filled with bugs, I'm sure. We're going to go through and get rid of them one at a time. There's a square root of lambda here, but it's not set, right? So what should it be? If gamma is greater than 0 and lambda is equal to 0, then square root of lambda is equal to 1. And that, basically makes us go away, which is the apply W minus I that the minimization over the sphere needed. If gamma is equal to 0 and lambda is greater than 0, then square root of lambda is equal to square root of lambda. Great. If they're both equal to 0, then we're doing LSQR, and apply W minus I never gets called. I guess we could do that. I'm not even sure we need to define it, honestly. Maybe we'll do that and then If it gets called by accident, there should crash. Okay. So now apply W minus I is set well. We're going to make sure now the square root of lambda in apply W minus I is set appropriately, which is what we want. Here we have apply A. So I think instead of all of these applies, we just apply A. We don't even need lambda. And like I said, we don't even need the sensitivity maps. There's no adjoints to check in this function anymore. Okay. Set a breakpoint so there's no like obvious typo bugs. Let's see if it runs through do checks. Square root of lambda, undefined function or variable. Right, so we're setting square root of lambda here. So we're going to have to set it up above. Because checks calls apply W minus I. I guess we're not going to be able to do that thing where if it isn't set, then it'll crash. Because we have to set square root of lambda equal to 1 if we're doing checks. Hmm? It's always good to spell your variable names correctly. Okay, so there's bugs in A, n samples, unrecognized variable name, n samples. Was it just used? No, this is, where is this used? Inside minimization over a sphere. There, okay. We're going to have to count samples in multiple locations. Fine. A passes. Apply A does not exist. That seems like a problem, doesn't it? Apply A does not exist. Hmm. Okay, I'm guessing it's the input arguments. K data apply A. Oh, I know. I know what the issue is. This is now a function handle, so we no longer need that. Looks like we don't need samples here and samples here. This function has gotten surprisingly short. Which makes sense because most of the beef is in apply A. Like most of the problem of least squares is the implementation of the matrix apply A. We don't need to do checks in Tikhonov because there's nothing to check. Let's get rid of that. Same thing with minimization over sphere. All right, run. All the things pass. This is exciting. We're making an image, maybe. Recon model based doesn't use apply A because it makes the A inside itself. And the A it uses is A top. That's okay. All right, so we've got an image getting created with lambda. And now it's time to go back and try to make an image with PDHG, or at least get PDHG running. So this, it turns out, is correct. How do I know? We could just get rid of that comment. Let's look at PDHG. What we need is prox of sigma G conjugate. Not TG conjugate, just G conjugate. That's all we need. Okay? Well, if we go back to the Moreau decomposition, that's what this gives us. We don't need to worry about any T's here. So that's what this does, this prox conj. It implements basically the Moreau decomposition, the generalized Moreau decomposition. I'm confused. Is there a bug in that code? N minus sigma oh no. That's right. Okay. Yep, that's what it does. So you pass in prox G and prox conj gives you out the conjugate of this proximal operator. So we can actually do it like this. Prox G conj is equal to at in prox conj at prox G in S. We need an X naught. Do we have everything? Maybe, but we got bugs. Sigma is not a recognized parameter. Too many input arguments. I don't think we need S maps. What do you guys think? Gamma, apply A, no S maps. Looks like I was right. Okay. I don't know that we need this. We might just set image equal to X star, or maybe just put image here. If we get that far today, I guess we'll find out. Sample mask. Tau. We don't have tau. Okay, we're getting pretty far. PDHG takes two step sizes, which are called tau and sigma. That's why, if you remember, we changed the other sigma in this code to gamma. So now tau and sigma are the two step sizes. Well, if you have tau, there's a very simple way to get sigma, and that's what this code does. So now we only need to set tau. So how do you set these things? That's the problem with PDHG. You really don't know how to set tau so that this will give you a reasonable result in like a lifetime of computation. So what do? Well, one way to set tau is to determine the norm of apply A, which you can do with power iteration. And then tau is equal to, I forget the requirement. I always have to look it up. Tau is not described in the inputs. All right, I guess we gotta look it up. Luckily, I got this set of notes that we just keep referring to. I think it's tau sigma has to be less than or equal to 1 over the norm of A. Norm of A squared. Okay. since tau sigma has to be less than or equal to 1 over the norm of A, the way to automatically set sigma, well, it looks like it has to be less than 1 over the norm of A. So the way that my code automatically sets sigma is just to take a value slightly less than 1 divided by the norm of A squared divided by tau. I think that's why PDHG takes the norm of A here. Right, so you either must supply sigma or you must supply the norm of A. Since we don't supply sigma, it's going to use the norm of A value that we supply, and it's going to calculate sigma accordingly. That's how that works. Will this run? Nope. Variable undefined S image. And where is that? Not enough inputs. Okay, I think now we're at the point that we're actually running PDHG. And it's crashing for reasons that shouldn't be too hard to figure out. Can I apply A to X naught? Yep, that runs no problem. Is G not defined? Oh, we need this. That's why there weren't enough inputs. When you forget to put the at symbol here, instead of passing in the function handle, what it tries to do is call G in this line. Well, there aren't any inputs being passed into G, so it doesn't know what to do. Error here. Incompatible dimension sizes. All right, so you've seen how this goes, I think. Like, now we're just going to go through the same process of debugging that we've been going through for a long time already. Tau is a scalar, ATZ is 65536, and X is 256 by 256. Okay, so I think what's happening is actually, I don't know why that's happening. ATZ. Why is that outputting a vector? Oh, okay. So now that we're using the same apply A, I forgot this part. Now that we're using the same apply A for both Tikhonov regularization and minimization over the sphere, this A both devectorizes and vectorizes, right? It always outputs a vector, a column vector. So here with image 0, we're turning it into a column vector here. I guess we could call this image 0 as well, minus well. And we'll turn it into a column vector here so that we won't run into the issue of these two arrays having different dimensions, different sizes. Now x should be 65536. Yep. Oh boy. Wow. What just happened? PDHG was running just fine. What just happened? I'm going to call this norm of n2 because when I put n of something in front, that always means to me the number of elements. So I'm going to call this norm n2. Should probably do it the other place. Here I used norm a. Okay. We must have been calling proxg2 a number of times already. So let's see if it crashes again at iteration 18. Iteration 18. Okay. So I think we're going to be able to get here with opt iter equal to 19. Conditional breakpoint. It'll only stop there when the condition is met. There is a spammer in the chat room. Six five seven 448. Okay, so this is gonna. It's at the proxy conjugate. That's where I needed to stop. Okay, I'm gonna say conditional breakpoint opt iter equal to 19. And why is that crashing only after 18 iterations? We'll find out soon enough. So I think this will run, just proxg1. That runs, great. How about proxg2? This crashes, right? In requires symbolic math toolbox. Oh, forgot to put a 2 there. Okay. This is wrong. Luckily, that bug let us take another look at that line. Ooh. So you might be asking, why does the objective value go to 0? With PDHG, the constraint is only met in the limit as the number of iterations goes to infinity. And in any one iteration, the constraint won't be met. Our constraint is an indicator function, right? We included that as an indicator function. So whenever the constraint is not met, the value of the indicator function is infinity. There you go. Okay, what's the size of x star? Okay, whose image? Figure time shows scale, absolute image 4. Boy, oh boy, that might actually be working. Now, you're seeing a whole bunch of noise here. Why am I not perturbed about that? Why am I like thinking this might be working? Well, these are the objective values, and they tend to be going down. Why are there only 18 of them? Oh, because after that they go to infinity, because the constraint wasn't met. Okay, the other thing is that we haven't yet searched over the step size or the number of iterations. If I change the number of iterations, let's say to 1,000, let's see what happens then. This is going to be a while. Let's just print every 10 or something. It's surprisingly costly to print stuff. Like you'd think that wouldn't be true, but actually printing to the screen delays things quite a lot. So by only printing every 10, we're reducing the burden of that. It'd be nice if we could print out a meaningful objective value. I haven't figured out how to do that with a generalized PDHG function like this. If we had implemented PDHG just for this particular problem, then we could output two things, right? We could output just this, and we could output how much this differs from that. But since we don't know what f and g are in the generalized function, what do you print out? Well, I'm printing out the objective value. Can I pass in? And in this code, I can't pass in an objective value function. Now I could change that, of course. I'm not sure if that looks any better, so I'm thinking it's not the number of iterations. It's probably the step size. I've got a trick up my sleeve about that. Let's call this image y, because we don't need here with x star, if we reshaped x star, it's going to store both x star and image. That means it's going to allocate new memory for image, and we don't need that. So we'll just let it overwrite, actually let it just change the size of image. I hope that all this does is change the sort of ancillary information that comes along with this array. and doesn't actually reallocate any memory. That's how I would implement it. Okay. So what to do? We're going to end here today. We got PDHG running. Let's check some stuff in. We've changed PDHG. Oh, we added some comments. Those are the changes we made to the dwork lib. See, this is going to be a huge number of changes now. Because we moved everything out of the sub-functions. Do checks is off, right? That debug is there. Let's make sure, good thing to do before we check things in, let's make sure that all our debug comments are gone. These are still there. I want those there. Any others? No. Okay. Okay, stuff is checked in. Convert spirit regularization to spirit bound. Looks like that's done. So what's left to do? This. Have find W return a value for gamma. Replace PDHG with PDHG with line search. So then we don't have to guess tau. Accommodate an array of gamma values. Have find W return an array of gamma values. I'm not sure. I'll have to think about whether that's a reasonable thing to do. I don't know that that's a good idea, actually. So then replace PDHG with generalized PDHG with line search. This is not yet published. This, like I say, is a trick up my sleeve. My student Alex has largely been the force behind this, and it seems to work very well. So we're going to give it a shot. These are to-do items. We're going to leave them as actual bugs in the code right now so that we're reminded about these things right when we start the next time. And with that, thanks for stopping by.